right, so this will be a quick going over of the back half of chapter 15, stuff that is not review for you guys. So let's talk about that now. Okay. We just reviewed all that already, so I'm not going to review it again. All right, I will bring this up super fast, albeit I don't think most of you need it, given your conversation of the vector addition that was up here already. Okay, calculating electric fields and forces. 1, draw 2, identify the charge. Make sure you're converting all units appropriately. Apply Coulomb's law. Sum the x's and the y's, aka 5 through 7 right here. Do vector addition. Basically, if you've got a couple of charges up there and want to know the force on one of them, it is all just, yeah, this is stuff that we as a review as well. All right, so electric field lines. The picture drawn on the screen is assuming that both A and B are entirely separate. As we said just a moment ago, we are going to look in just a second to see what if they are in the same area. So the first couple of rules up here are 100% necessary for the new rules as well. Number 1, electric field is always drawn tangent to the electric field lines at every given point. Meaning, obviously that's kind of, well, it's obvious when it's straight. What if instead we had a situation like this, where the electric field line looks like that? Okay, well, that would mean that the electric field at the spot at the very bottom, right down here, is tangent to that point, so there is the direction of electric field, and there is the direction of electric field, and you get the idea. Those of you viewing online are not seeing what I drew just a minute ago, but this is meant to show that weird winky face, whatever. But that very similar thing to what we just drew up on the board. Electric field lines are drawn tangent to the lines at those respective spots. Number 2, the number of lines is proportional to the field strength. So if, like in this particular case, you have the same amount of positive Q as you do negative Q, simply put, you want to draw the same number of lines, leaving the positive as is going into the negative. What's up? Sorry to interrupt.
No one have any idea if I left my calculator here by chance?
Check. I have not seen it.
Okay, thank you. Yeah. Okay, thank you. All right.
Okay. Look. So if there, of course, we'll see in just a minute, what if the charges magnitudes are different, but the name suggests if there was twice the Q over here, there would be twice the number of lines leaving that, or if there's some weird ratio, then the ratio must remain exactly the same. Okay, so drawing field lines. What you're looking at over there on the right side is a complete electric field of those two scenarios. So how do you know what to do? Number 1, lines must begin on positive charges and end on negative charges, or it doesn't have this up here. They can also go out to, I'm going to put this in air quotes because it's not quite real. They can go out to infinity or come from infinity. By infinity, I am simply saying like this line right here. This line is going out towards infinity. Now, in truth, it is actually wrapping around way out here. We're just not drawing it way out over here and coming back over on this side right over here. Number 2, as the name suggests, the number of lines must be proportional to the charge of the magnitude. Meaning if I have, man, they drew a lot of lines here. I would not draw this many. I'll show you mine in just a second. So 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. If you have 24 on the left side, you should be drawing 24 on the right side. That being said, you can draw these a little bit easier. And number 3, the general rule that electric field lines do not cross. I think they're going to say it in a second, but on the off chance, I want to make sure they hit it. Okay. Yeah, let's go from here. Okay, they did not. The other thing is, and this should make sense, lines should leave perpendicular to the charge. Why? Well, at this location right here, I mean, all electric fields are a sum of multiples. But as you get close to this particular positive right here, technically, what does the magnitude of electric field head towards? Remember your equation in, what is the equation for electric field in a, what's the equation for electric field in a variable field? How do I calculate E in a variable electric field? KQ over R squared. If you'll remember, that comes from this. Electric field is Fe over Q test charge. But what is Fe in a variable? How would you calculate Fe in a variable field? Coulomb's law. KQ of the source, which we don't usually write source, we'll just write Q, and the test charge over R squared, and there's force electric divided by Q with the test charge. So cancel, cancel, giving us this guy right here. Now, I know I mentioned this on Friday. I'll say it again real quick. Okay, when doing the uniform electric field, you can quickly see from the algebra that it simplifies out to the force electric is equal to QE. And actually, in this particular case, it again works out the exact same way because it started the same way. Force electric is equal to Q times E. And of course, I know that because E is this mess. K times Q over R squared times that Q brings me right back to Coulomb's law. Point is, if you use this whole mess and calculate that it's, say, 100 newtons per Coulomb, please do not use Coulomb's law a second time if another charge goes in. You should just be using this guy right here for that particular location. Now, so R is what the magnitude depends upon. You saw that in the picture up there, because what happens to E negative as we get closer and closer to negative? Gets greater, right, and positive vice versa, right? Further and further away, it gets less and less and less, and that's because of this R squared right here. So the question I had just a minute ago is, why should these lines leave this completely perpendicular? What happens to the electric field as I make R essentially closer and closer and closer to zero? Limits right here. It heads towards infinity very quickly. It gets very, 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 very big relative to anything this is over here. Yes? Okay. So here's how I would draw this if I were you. Number one, I personally always try to make sure that the lines are evenly distributed around the charge for the most part, without wasting my time on drawing, as the picture showed just a minute ago, 24 different lines. So I would probably do something like this, and then I would do this, and this. And what happens to the curvy nature of them as it gets further up here? More curve. Less curve. Because it's further and further away from the other charge. It's closer to the charge at hand, so it should be closer and closer to... Let's go back a little bit here. Now, as it gets over to the left and right sides respectively, this is where I start drawing towards infinity. Why would this one go to the left? Doesn't negative pull to the right? So why would this one always go to the left?
It starts at positive.
Sure. The positive pushes to the left, negative pushes to the right. Why is the total always to the left? Yes, Gabe. It's always going to be closer to the positive, and therefore the positive will always be stronger, and so yes, it'll also go to the left, and vice versa over here. And finally, I would usually draw infinite lines for these guys. Infinite just meaning I'm not drawing connected to anything. And like I said, notice that lines curve more as you get closer to the other charge. They curve less and less all the way over here. So, how many lines did I draw leaving the positive? I believe it's 8, right? 8. 1, 2, 3, 4, 5, 6, 7, 8. And how many are going into the negative? 8. because these are assumed to be equal charges. Make sense? Why don't I just why don't I do the QR code thing at the end? Just don't let me forget. Gabe, what's up?
The curves in the middle,
Mhm.
they like just keep getting sharper and sharper. Like,
I'm sorry, with what change?
so like, if you the electric field going like out of the positive,
Uh-huh.
if it's not quite going straight up, but just like barely,
Barely to the right.
yeah.
It probably look like this. Something like that.
Okay. It's like, is there a point where it switches from? Never mind.
One other thing to mention about these graphs is something that we talked about with electric field lines last year, and that is how can you tell with an electric field what the magnitude of that field is? Like looking at pictures, looking at a simple picture like the uniform one drawn on the board, or these variable ones from just a minute ago. Thought we did it up here, did we not? All right, well, okay, we didn't. So what about electric field lines would tell you their relative magnitude? Not length on a field line. Line density, otherwise known as space between the lines, right? So in this particular case, the line density, aka space between the lines, remains constant, so that's what tells us that this is uniform. Whereas here, line density, the further away, decreases. Yes, you can do the exact same thing looking at these pictures. This should be up here if I can move it. Can I move it? Oh, you're gonna let me move it? You're not gonna let me move it, are you? All right. Right here, like for example, I should be able to, just drawing this dumb picture, go, hey, here's A, here's B, and here's C. You should be able to quickly be able to identify where the magnitude is about the strongest. Where would the magnitude be? A, followed by B, followed by C. Now, the only way that works for you to be able to do that is because you're hand drawing these, is if I make sure to symmetrically represent these lines. Could I technically draw one of these with 10 of them over here and 2 of them over here? Technically, according to the rules, yes. However, is that going to give me deception as far as which one is actually stronger, left or right? Absolutely, it is, unless I draw them evenly. I'm not going to be able to see that A is the strongest, B is the second strongest, and C is about strong. And even if I go over here and put D, how should A and D compare? The same. Why does it make sense that they would be the same?
Because they're the same distance away from.
Right, and these are the exact same charge, right? Whereas this guy, in this case, would be way stronger. There is E positive, and there is E negative. Over in this location, there is E negative, and there is E positive. And I just basically flipped those two locations because of the distances in question. How are we feeling?
Wait, why would that be E negative? Why is it going towards the negative charge?
Which way does an electric field go with a negative charge?
Oh, well, okay, never mind. I was thinking like you had it as negative, so then.
Nope. E negative would just be caused by the negative. Yeah, we don't have any test charges up here
I
whatsoever
understand what you're doing.
right now. All right. Let's look at some other pictures here. What if there's two positives? Well, if there's two positives, lines do not bend towards each other. They would bend away from each other. Why? Bill, if you look at A right here, there would be, I'll call this guy 1 and this guy 2. There is E1, and of course there is E2. But which one's definitely going to be stronger? E1, because it's simply closer. Notice once again, we start These should all be drawn perpendicular. Okay, we start as though it's coming out from right here, and we draw once again an even number on both sides. So I don't like how many lines they draw because I would not do that if I were you. So let's go ahead and show that one again just a second. What if it was positive and positive? Why will I not draw any lines in here? I don't, but that's not what's important. Yeah, so it's electric field lines always start at a positive or infinity and end at a negative or infinity. They will never start just in the middle or terminate randomly. Technically, the best way to draw this is not what we do with electric field lines. It would be that right there. This is not terminating at a negative or infinity, so we don't draw it in here. We would draw it something like this. So here's the easiest way to do it. Okay, you go, all right, which way would this charge normally make it go? Well, it would normally make it go here. What is that going to do to that line? It's going to bend it further and further away, right? Not bend it towards, bend it further away. So that would be like this. Just like that. This would normally go straight down. Which should bend faster? This guy or the one that I'm about to draw? Which one should bend faster? The right or the one I'm about to draw? The one on the right. I should not have drawn that straight at all. Now, I understand why they did what they did in basically drawing it no line going left or right, because by my choosing to draw this line right here, it automatically makes it unsymmetrical. I've got 3, 3, and 1 on the left, and I can't draw the 1 on the right. But yeah, that's just fine right there. Now, what happens to this picture if this is twice as big? What happens to this area? There's more lines, sure. What happens to the relative strengths?
It would be less.
What would be less?
The strength
Of which one?
of the two.
Why?
Because when you have more lines, there's going to be less curvature.
That's not mean this. That doesn't mean the strength goes down. If I double the charge, what should happen to the strength of the electric field? Yeah, it should be twice as big. So now, which one's probably going to have more say on the surrounding area? This guy or this guy? Definitely this one right here. So simply put, the first thing is kind of this line right here is the line of equilibrium. Why? Because if I look right here, this guy would push that way, this guy would push that way. So in total, which way does electric field actually point? Straight up. But again, we don't draw lines starting at nowhere. We always start them at either positive or at infinity, so you would never draw that line right here. So if this was a 2, let's go ahead and erase this for a second. Oh, you know what? We're going to do this differently. Changed my mind so that you guys have access to this picture later. Let's go ahead and go here and copy. There we are. All right. Now we'll erase. All right, and the one on the left will be twice as big. So how am I going to do that? Well, my lines are going to go straighter, longer. Well, that's not very great. These lines are going to curve much faster. All right, I just drew 5 lines on the right, so I need to draw 10 on the left, and I need to be very cognizant of trying to spread it out as much as possible. So I always start with the small side one. So let's go, how many I got? I got 4 left then, so. we are. So you can see that the lines on the left side, there's twice as many, and also they go straight longer. They don't bend nearly as much because they have a much bigger impact doing that twice the charge. It moves that line in that particular direction. This is kind of what it would look like if you had twice the charge on opposite charges. Once again, you will notice that all of the lines either start at positive or infinity and end over on negative, but actually for this guy, all of them have to end at negative, so you can actually draw twice the number of lines, leaving this guy right over here. So we've got 1, 2, 3, 4, 5, 6, 7, 8 coming in over here, which means there have to be 16 leaving the left side. Notice once again that all of these guys over here say straight longer because they are because it is a much more powerful field, and all these bend super quick over here on the right side. Questions, concerns? You might be expected to draw a handful of these, just the basic ones. Mostly, though, it's trying to interpret what this actually means. What does it actually mean? Well, I should be able to, like I said before, look right here, and very quickly you should be able to identify from the picture what has a stronger electric field and why does that make sense. Which one has a stronger electric field?
The one with the smaller distance.
Right. And why does it make perfect sense that this would be the stronger electric field? It is right next to these two charges, so of course they are going to have much larger amounts of magnitude. Yes.
Okay, so I understand where they are and like why they would have like a stronger electric field because of the lines, but I don't understand how you know to like where. How do you know where to draw your lines? Like you start at the positive.
My general rules are as follows. 1, the line must leave perpendicular. So what I do is I think about which way it would go if there was nothing else, right? So that's what I did when I was talking about this guy right over here. Okay, when I was talking about this one a minute ago, specifically this guy right here. Which way would this go if nothing else was around? Straight that way, right?
Yeah.
Next, I consider which way will that make the line bend? Away because it's pushing a positive away. Yes? So that's what causes it to curve that way. Okay, now where exactly I drew these around, my main rule was just symmetrical as much as possible. So in my head, I'm trying to pull off ratios. I'm trying to go, all right, well, I'm going to put 3 on top. In general, I try to cover like left, right, up, down, and like the corners, me personally. With the exception of if I have to draw like a ratio of 2 to 1, keep in mind if I draw 20 arrows coming in over here, I've now got to draw 40 arrows over here coming out. It's going to make it a lot more challenging. So give yourself a little bit of a break. Like in this particular case, right here, I only chose to do 5. Now, really what I probably should have done to space this guy out a little bit better was split the difference like right here. The other thing, and it takes a little bit of time to get good at these, you know me, I'm not the most artistic person, so the fact that I can draw some of these at more curves than others is taken a little bit of practice. I'm not expecting perfection here, right? They're all leaving perpendicular, right? You'll notice these lines over here are curved more because they're closer to this side. As they get further away, they're curving less and less. I'm trying to be evenly distributed. Yes?
So the field lines tell you how much force they put, or
field lines tell you the relative amount of electric field at those 2 areas.
So
in terms of not force but electric field, keeping in mind obviously that would be directly related to the same amount of force if you had the same amount of charge being put in it.
So in that middle area, would there be no electric field?
No, remember this is what I was talking about before. There absolutely is electric field. Just the general rules of electric field lines mean they will not start at some place other than positive or at infinity. So why is there nothing in the middle? Well, technically what should be in the middle is this, but due to the rule I said a second ago that they can't end at nowhere, we could not draw them at all here. Does that make sense? You can put more in the middle, but these will bend really darn hard towards that equilibrium point. There's kind of a dotted line right here. That dotted line represents where the X would be in equilibrium. And why is the X in equilibrium here? Well, this has more charge, but that's closer over there. Other questions, concerns?
Can you draw another line on the right side so it's even?
Why don't I just do this? What's that? Yeah, because if I drew another one, actually, I shouldn't draw.
Yeah, I know. That's what it was bothering me.
Fair enough.
Okay, thank you.
No problem. All right. Other questions about electric field lines? Rank, I mean, we just talked about this. Rank the electric field at points A, B, and C. From largest first. If 4 is the answer, then this entire conversation was a dumb conversation to have. What's the answer? 1. A, B, C. What is the electric field strength at C? 0. Because they're equal magnitudes, equally in the middle, they should cancel each other out entirely. All right, let's talk about properties of electromagnetic equilibrium. All right, so this is if I have a conductor in electrostatic equilibrium. Now, the thing about these rules is, let's see if I have any better luck with my examples today with the electric field. Basically what it's saying is I have an electrostatic conductor in equilibrium. I have a metal object that I just put into equilibrium by conduction. So I take something like this. Yeah, we're doing better today. Okay, so what are the rules? The electric field is 0 everywhere inside the conducting material. That's actually, I hate the fact they started with that one. That's not the right one to start with. Also, I don't know why that picture's down there. This feels very out of order. We should start with 2. Number 2, any excess charge on an isolated conductor resides entirely on its surface. Let's talk about why that is. Here I have a metal sphere that some negative got put onto. Now I'm not going to draw, obviously we know that the metal sphere has a bunch of positives and negatives. I'm only going to draw the excess. So here is the excess charge. What are those excess charges doing to each other? Repelling. And when are they going to stop repelling? Never. They're never going to stop repelling. So what are these charges going to do? Try to go as far away as possible, which is going to end up out there. Okay, but the next question, of course, becomes, what if you have a positive charge? Now, before you tell me it's the exact same thing, do positives move? No, but reminder of what I said a minute ago, because it's very important. That is, are there other positives and negatives inside this material? Yes, very much so. Are there a bunch extra positives and negatives that are not the excess ones? Or in other words, why is an object negative? Why is an object positive? Less electrons. We didn't add protons, we took away electrons from the total. Now when you actually look at the total, this is like nothing relative to that. The excess charge is practically nothing. Why? Can you visually look at an object and go, yeah, that guy obviously has more electrons?
Yeah.
I mean, not this. I'm saying literally look at this ball, and you know that this ball has more electrons or less electrons by visually looking at it. Shut your face. All right, no, you can't look at it. You're not going to be able to. The amount of protons and electrons that are there relative to the excess is such an infinite percentage that you would not be able to weigh the difference. You would not put on electrons onto an object, have it on a triple beam balance, no matter how accurate the triple beam balance, and ever go, well, obviously this one's heavier because it has more. Okay? The percentage, it's basically what percentage of electrons and protons in a charged object are evenly balanced? Basically 100%. The actual answer is 99.9999999, but I'm not going to get into the actual percentage. Point is, Keep in mind that there are still negatives up here, right? And what is this positive doing to those negatives? So if it pulls a negative from this area right here to that area, what happens to that area? What happens to this guy? It becomes neutral. And what happens to the area that it just pulled the negative from? It just moved the positive. Now, did it actually move the positive? No, it moved the empty space. That being said, for our purposes, doesn't it look like the positive is going to move? And so it's going to keep pulling, it's going to keep pulling, it's going to keep pulling until that empty space is where? On the outside. So excess charge is on the outside. Therefore, what charge is in the middle of it? This is what's known as the idea behind, if you've ever heard, a Faraday cage. A Faraday cage is something where a person is in a ridiculous electrical environment. You maybe have seen these on some old pictures. Okay, you're welcome to look up right now. But a Faraday cage is a person could be in a lightning storm. If they are simply inside of a metal cage, they are 100% protected the entire time. Because if the excess charge resides on the outside, what charge is it on the inside? Neutral. So you can actually weirdly defend yourself against an electric shock by wearing a plate of armor. Now, that being said, the plate of armor will 100% protect you from the electric shock. What will it not protect you from? The heat. The temperature that is created internally by that particular thing. So, as long as you have enough open space, like a giant cage, to bleed off that extra heat, you could stand in a lightning storm inside a Faraday cage. I feel like I keep talking about this. We might as well find something here.
This doesn't feel right. I feel like that.
All right, fine. We'll find a video then.
Wait, but can't you not touch the metal?
Oh, 100% you can touch the metal.
You can?
Now, here's the thing to consider, okay? Here's what you're trying to think of. You're thinking the metal is kind of all connected, right? If I have a plate though, okay, when I say the excess charge resides on the outside, once again, what percentage is it that's actually got the excess charge? Less than 1%, and it's on the surface. So there's all of this layers of metal on top. What charge are they? Neutral. You're completely fine with a neutral. All right. So Faraday cage. All the time. Where's the slow-mo guys that did it? Here we go. I think this is them. Oh, it's not. This is not the slow-mo guys, but this is an idea. So we talked about a Van de Graaff generator last year. This is a gigantic Van de Graaff generator. I hope you feel better. Otherwise, this is a really crappy example. 100%.
Wait, that.
Yes. Here, let's find another one. I think I said the slow-mo guys did it. Well, they used. Come on. This takes one in.
I know.
Oh, this is not the guys. Hold on.
They were just like,
There you go. So you could surround yourself in armor that essentially is a cage, as this particular individual is about to show. Come on, there's a reason I use an ad blocker for school. I don't use an ad blocker at home. I'm not a jerk.
Hello, I'm Gab. I'm Dan. Welcome to the Super Slow Show. Bit of a late evening video here.
Yeah, there's a reason for that though. Yeah. Something I've never wanted to touch as part of what we do, because it's very dangerous. I don't know enough about it. Sharks. Right, it's not going to be sharks. It's got a huge. We were done. Bit.
Scariest charge now.
Yeah.
So these are the Faraday cage.
Plasmids.
Just like.
Watch this thing. Oh.
Literally looks like powers in a video game.
Yeah. It's very Bioshock-esque. It's like a big David plasmid.
It really is.
So all along him, there are wires sticking out to grab extra charge. Well, those are actually plastic right there. But he has wires in the
You can
gloves.
see a little shimmering above it.
There's probably also an insulation of the glove that will insulate it from electric shock as well as
that plank.
So the electricity hits the staples because it heats up and burns the wood.
Yeah.
All right. All right. So if inside the charge it's neutral, what electric field is created by a neutral charge? 0. And thus, actually, that's why I said it's kind of dumb that they started with 1. They should really start with 2, leading us directly into 1. And if there is no electric field on the inside, that would mean if you put any charge on the inside, it would have what kind of force on it? 0. So would charge on the inside of an electrostatic conductor move? So would someone inside a Faraday cage have to be afraid of electricity actually getting them? No. Temperature, yes, but electricity, no. Next, the electric field outside of a charged conductor is perpendicular to the surface. Now this is somewhat similar to the idea I talked about a second ago, talking about the electric field lines. The slight difference here is in the last example where I talked about electric field lines, we were dealing with an atomic or microscopic scale. Here, we are actually dealing at this particular level, that the electric field lines go perpendicular to this guy right here. Okay? Why? Well, because if they didn't, let's look at the opposite. If there's an electric field line pointing that way, there would be a net force on positive going in the x, and so it would move. Yes? And negative, of course, would go to the right. When would it stop doing that? Once it's evenly spread out, aka it's in electrostatic equilibrium. Once it's in electrostatic equilibrium or evenly spaced out, lines cannot leave at any other angle but perpendicular to a surface. Meaning if you had some weird surface, you could make up a surface like, I'm just going to draw a weird line here. There it is. And I should be able to pick a random spot along said surface, like this guy right here, and you should be able to tell me the direction of electric field at those various spots. Okay, last one, and quite frankly, one of the most interesting and kind of hard to wrap your mind around rules. So there's 4 rules, okay? These 2 kind of go together. That one kind of goes with the last example we did. And here is the biggest and probably most important one right here. On an irregularly shaped object, okay, aka it is not evenly distributed. So it is not a perfect sphere. It is not a straight line. Irregularly shaped charge will always accumulate at sharp points where the radius of curvature is the smallest. In other words, what they're saying right here is, let's say I have 2 charges of equal amount. Here I have 2 negatives. Of course, they push directly away from each other on the left side. Here, they also push directly away from each other. But if you split those components, not into x and y, but how much is perpendicular and how much is parallel, this would be perpendicular, that would be parallel. Let's go perpendicular, parallel. So this is force parallel, this is force perpendicular. And here, force perpendicular has increased and force parallel has decreased. Now, why does that matter? Are these charges going to move perpendicular to the surface? That way. Probably not out into the air without a great amount of effort. Will these charges easily move along a conductor parallel to the surface? Yes. Since there is more force along the surface, it's going to push them further away. Meaning, I don't like that they have it on the same object. If I have a piece of metal that looks like this, and a piece of metal that looks like this, and I put them in equal amount apart, in both cases, this left side, they can easily move along that left side, spacing themselves out. Yes? Can they move nearly as much along this surface, spacing themselves out? So are they going to be closer together? So is a charge going to accumulate at sharp points? Yes. And to prove this, this is why I have been using a giant metal sphere up here as opposed to this guy right here. This has sharp points. Sharp points will cause shocks way easier than round ones. See if I can do it today. Did you hear it? Stupid mower was going off for a long time. Try it one more time. There it was. Did you hear it? Sharp points, it will accumulate and therefore shock. Whereas, if I attempt the exact same thing with a round point, it's more spread out, and so you are not going to get the shocks there because they can't accumulate to a particular area. Or, I think this is the next one they're about to do, so I want to make sure, yeah. Here, I'll come back to 47. You guys have probably heard about lightning rods, but more than lightning rods serve two purposes. The first purpose that a lightning rod has is not what you actually think. It's the second one. The second purpose that most people think with lightning rods is it puts a metal rod up there so that if and when this thing gets shocked, you can direct the electricity where it's supposed to go. That's probably what most of you have heard about lightning rods, yes, or believed yourself previous. The first and most important reason is this. If you make that into a sharp point, where is the charge of this entire building going to accumulate? At that sharp point. And is it going to be able to hold on to all of that charge at that location? Which is meaning if I make a sharp point, it's now going to bleed off into the air. So is this going to stay nearly as charged? No. So it doesn't stay nearly as charged. So actually having a lightning rod not only directs it where it's supposed to go, having a lightning rod to begin with prevents lightning from ever happening. Because more lightning, more charge can build up in a flat surface. So take, for example, a lightning strike in an open field. Can you build up a huge amount of charge in the ground? Yeah, the more the electric field up top, you pull more and more and more charge into that area. And if it gets to enough charge, boom, it pulls those electrons out of the ground and you see lightning. What happens with this church standing nearby? Well, it tries to make it more and more and more charge, but since we got this little sharp point right here, what happens to the charge? It bleeds off into the air. So can the total charge of this go up enough? And therefore it does not actually get a shock on that particular building at all. Yes?
So you're saying that it bleeds off into the air, but like how does, so like does
What
the
do
charge-
negatives do to other negatives?
They repel.
Repel. Why don't they usually go into the air? Air's an insulator, there's not a lot of room to go. But if I accumulate a ton of negatives at one point, does that put a lot of force on them?
Yeah.
So could it push those negatives out into the air?
Yeah, but why are they going to that point?
This is what we were talking about, that
Well, yeah.
charge accumulates at sharp points. If it has all of the options in the world in equilibrium, it will always accumulate at sharp points for the reasons discussed over here.
So these rules apply when it's equilibrium specifically, so are they?
Yeah.
And can you remind me specifically what equilibrium is?
Sum of forces equals zero. It's Newton's first law. Now, let's go all the way back. I hear you. I'm not just going to stop at that and just say that's it. Equilibrium is Newton's first law, and also something else that we've talked a ton about, and that is equilibrium, sum of forces is zero, but what is equilibrium when you deal with a crap ton of objects at the same time? if you guys were all bouncing around at random in this room, what would equilibrium look like? Evenly spaced out, assuming there's nothing else at play, or net forces are zero. Okay? But what if there was a general pull in a particular area? For example, let's say there was like 4 times the amount of people in here, or even 10 times the amount of people. There's 100 people in this room. You can actually start to see it. Why would people start to accumulate at sharp points? Why would some people accumulate in these pockets right over here? Because they'd be stuck. They'd be trapped. They'd be pushing on them all the time, and it would kind of keep them in that particular area. And there's really no room to go, so they would hang out in those. So what do charges do? The exact same thing. Charges end up, think of that sharp point right here. Okay, this is actually really good. I've never used this example before, but I think it works really well. Think of this sharp point right here like one of these alcoves. Why can't the negatives go back down this way? Well, they could, but is it very likely that they end up going down this way?
The other negatives are pushing them back up.
Correct. And also, keep in mind that the negatives reside out on the surface. You can't like cut it off to go in between, right? Because a negative on this side of the pole is not going to cut through the middle, because what are the negatives on the other side of the pole doing it? Shoving it back this way. So they're all going to remain on the outside. So where is the easiest place to get through? Where's the most room? Where you have the least amount of curvature. Or I draw like a weird shape here. Where could you possibly get the most accumulation of charge? In like alcoves like this one. Or in this guy right over here. Why are we not going to get a huge amount of accumulation of charge within there? Because there's a room. There's room for them to spread out in those particular areas. So it's a little bit backwards of that then. Where can you actually accumulate the most charge between these two surfaces? This one, or let's say this one. It's actually, this is where you can accumulate the most charge, because it's not going to bleed out into the air and you're not going to lose charge nearly as easily. That's why I tried to show this example a second ago. Whereas this guy will get an electric shock because it pulls charge to these sharp points, like this corner right here. You get an electric shock in that case. Would we ever expect an electric shock if that guy's up top? No, we would not expect an electric shock in this case, because the charge can all evenly spread out. It's not until it like straight up actually touches that we get it to pull off in that particular case. All right. Ooh, where are we at? I got the last one, but it's a rough one. All right. Silicon oil drop.
Oh God.
No, it's not. This is actually not the hard part. This is easy. This is super easy. This is how Millikan oil drop essentially worked. Millikan oil figured out this really, really clever thing. Hey, I'm gonna look for drops of oil that are going at a constant velocity. Because constant velocity means what about their forces? They're equal. So in this particular case, he would turn the electric field off. Nothing would be on, and he would watch water droplets that would just be going, oil droplets that would be going at a constant velocity. Why? Gravity would pull them down, and drag would push them up an equal amount. Okay? Next, he turns on the electric field, pointing it down, so that force electric points up. Yes? And he looks for the exact same oil droplet going the exact same velocity. Because if it's the exact same velocity, what's true of the magnitude of the drag? It's the same amount. It's just pointed the opposite way. So this drag that's right here is equal to that drag right there. And so you can use this to kind of compare and use multiple equations here. Ultimately, once again, what Millikan oil figures out is the quantization of charge. That all charge comes in a magnitude of 1.6 times 10 to the negative 19. All right. Van de Graaff generator. Here's a picture, by the way, of a Faraday cage that we were talking about a second ago. That is the Van de Graaff generator right back there. We will get that guy out tomorrow and talk and use a few examples of it, and also try to once again confirm some of these rules with actual real-life experimentation. I think that's a very important thing in physics. If you're just sitting there and just trying to like for example, especially that last rule. Charge accumulates at sharp points, and you just try to beat it into your head. Great, but it's really helpful to see that actually be the case in real life to go, well, one way or another, whatever my belief is, this is what happens in real life, so I better try to figure it out. So the Van de Graaff generator, in a nutshell, uses some of these ideas. For example, it uses sharp points because charge will accumulate there. It then runs a belt. Specifically, this charge guy right here runs the belt. It frees electrons, and those electrons jump into the ground. Well, that makes this guy right here positive. As it comes up, that positive is coming by this guy, and what charge is the dome going to start as? Now, what charge is that dome right now over there? Neutral, right? But if positive is coming right next to these little guys right here, where what's accumulating negative, what are those negatives going to do? Jump over to this positive belt right here, making the belt now neutral. But it's making the guy up here positive. And the more we run the belt, the more positive we pull from the top. So what charge is the top in total? Charge is going to be positive on top. And you can get more charge off of the top by running the belt faster. Okay? By running that belt at a higher speed, you can get more out of it. Now, eventually, you can't pull off positive forever, because what's this guy going to eventually do to the surrounding air? Pull negatives out of the surrounding air while negatives are going in there, leaving it at a net same positive charge up here until it gets some donation of charges, like, for example, is happening right here. This Faraday cage is what charge to start off with? Neutral. So that is very positive. So you should be able to point in the direction that the charge is actually going, right or left. It should be going that way, right? Pulling the negatives up in that general direction. All right. This next conversation is a painful one, and also we're going to try to keep it quick. And the reason we're going to try to keep it quick is, one, it's painful, and two, it becomes much, much more important a little bit later on. Let's talk electric flux. Now, electric flux is a concept that helps us to understand some other things that's going to help us a little bit easier. Here's the best way to understand electric flux. I'm going to begin with gravitational flux. Okay? Basically, which way is gravitational field lines in this room? Correct, straight down. Okay? Electric flux is trying to get an understanding of how many electric field lines are here. Meaning, if I represent gravitational field lines as being one gravitational field line per square sitting right in the middle, okay, then how many lines would go in one tile? One. Okay? And if I doubled the amount of space, what happened to the number of lines? Two. We would say that electric flux has doubled in this particular case. It's a way of talking about how many lines go through a particular area. Okay? Now, can we get the exact number of lines? No, because we make it up, sort of, right? But watch this. Even if I represented gravitational field as being 2 lines in a particular area, and then I double the area, has the flux still doubled?
Yeah.
Yes. So, flux represents how many lines are going through a arbitrary area. Arbitrary meaning you get to pick it. Okay? So I picked a tile, and I picked 1 line to begin with. Then we say, what if I picked 2 lines? Okay, but if I pick 2 tiles, it goes, instead of 1 to 2, it goes 2 to 4. We've still increased by the same number of lines. We've still increased by the same amount of flux. Yes?
So flux is just like a ratio?
Sort of. So think about it like this. Electric field is proportional to how many lines per a unit area. So I said a second ago, I said that for a gravitational field, we'll represent it as 1 line per 1 square, right? So that says, if I double the area, do I actually double the amount of electric field or gravitational field? No, I've got twice as many lines only because I have twice as many area. Yes? So the strength doesn't increase with area, but right here, the number of lines, just using some algebra here, is proportional to both electric field and area. So let's say, for example, this is I know this is fake, but let's do it. Let's say the left side of this room weirdly had half the gravity of the right side of the room. Okay? We're not going to make it difficult. We're not going to double your weight. Let's just go ahead and say this is half. So you can bounce around like a crazy person over here. What would that mean about the number of gravitational field lines on the left side of the room versus the right? So over here, you'd have about half as many as you would over there, right? So here, let's say it's 1 per tile. Over here, it's 2 per tiles, okay? Now, same type of conversation. What happens to the number of lines as I double the area or triple the area? The number of lines should double and triple. So, number 1, the gravitational field, or electric field in this particular case, obviously affects the number of lines. Twice the gravitational field, twice the number of lines. Yes? And twice the area, twice the number of lines. Flux, this is an iota, I believe. No, it's a phi. That's a phi. If you want the easy way of drawing phi, here it is. Draw an eye in a circle. Okay? That represents the flux of electric field. And ultimately, like it says right here, is a representation of how many lines, electric field lines, there are. Another good way to put this is if you think of electric or gravitational field lines as water, okay? It would be how much water would you get if you have a certain amount of area. So imagine this entire, instead of gravitational field lines pointing down, imagine there's a torrential downpour on Spainhour right now, okay? And he's got his hands out like this, okay? I've got a certain amount of water coming through my arms, yes? And as I double the area, what would you expect about the flow of water? You would double the flow of water in that particular case. Units are, yeah, it's just going to be, actually, I don't like the way they put this. Electric field is newtons per coulomb, right? So newtons per coulomb. And area is simply meters squared, so meters squared. Just multiply the two together. Okay, great Spainhour, why? It's a good point. Now, there's one other way that we could change how much water goes through this area, and it would be like this. Okay, if gravitational field is pointing straight down, or water is coming straight down, of course I could increase or decrease the area, right? That would change flux. I could increase or decrease electric field or gravitational field, meaning the flow of water. If I double the flow of water, twice as much is going to go through. The third thing that I could do, though, is I could take this area and rotate it. And what happens to the amount of lines or water coming through my arms now? Less and less and less until zero. Absolutely zero in that particular case. So this angle right here, this angle is how far the lines are from the normal of the surface. Meaning, they don't draw an amazing picture here. So let's try this again, so I can not lose all of these. Electric field lines are going down. This is the surface that I've decided. Normal of a surface is just 90 degrees. So what is the angle between the lines coming down and my surface? Oh, and my normal line, what's the angle? Zero. This line and this line are at 0 degrees. That's why they're using cosine. If instead I turn this surface like this, 90 degrees, cosine of 90 is 0, no electric flux. Okay? And finally, what if it's somewhere in between? This is the angle that you choose, from the line to the normal line. I admit that is a weird way to measure angle. There is an advantage to it later on that I'm going to leave alone right now. Yes?
What's the dotted line?
The normal line. So like, if you draw any surface, the normal line is just what's 90 degrees of that surface. So I drew a surface right here. So like right now, obviously, the ground, which way is the normal line? Up and down. Up and down. It's just, yeah, it'd be down. So obviously, gravitational field to that normal line would be 90 degrees. Whereas if gravity's coming this way and you were dealing with a hill situation, right, then the normal line would be this, and the angle is from that gravitational field line to the normal line. Now, why didn't they just use sine and talk about the angle here? Well, there's a whole conversation for that we're not going to worry about for right now. Like I said, this is a complicated topic that I want to cover real quickly. Ultimately, it's just saying this: if lines are coming straight down and I start rotating, what happens to the number of lines going through my arms? It gets less. All right. Not going to worry about that right now because you got some homework there. Now, Gauss's law uses this exact same idea. How do we calculate the size of electric field? You'll see the equation over there on the right side. Yes? So, how do we calculate the electric flux? Now, watch this. A Gaussian surface is an arbitrary shape that you make up. Okay? How many lines would I have to draw coming out of this cube? Doesn't really matter, right? I'll choose 4. Okay? But here's the deal with the Gaussian surface. I have chosen a sphere. What would happen to the number of lines if I make the sphere smaller? Should be still the same number, right? Now that's an easy way of looking at it. But electric flux is defined as E times A. What happens to E as the surface gets smaller? Increase or decrease electric field if you get closer to the circle. Try again. Closer to the charge, if I made this circle smaller, it would get bigger and bigger and bigger. By how much? 1 over r squared. Because I'm getting that smaller, right? But what happens to the area of the sphere? It also gets smaller. By how much? Also r squared. Because here is the equation for E. Here is the equation for surface area of a sphere. Yes? So what happens to r squared? And that goes with the thing I said at the beginning, the way easier way of looking at it, and that is what happens to the number of lines if I make that sphere bigger or smaller that are leaving. It stays exactly the same, which means what happens to electric flux? It stays exactly the same. Why does it stay exactly the same? Because E, as you make that closer, gets bigger, but A gets smaller. By how much? R squared in both cases. So the actual electric flux is 4 pi Ke over Q. And when you look at that equation, notice there's only one freaking variable in it. That's Q. So if we rearrange this, or if you remember, Ke, or maybe you don't, maybe we didn't talk about this, Ke is actually a different constant or a combination of another constant, and that is, Ke is actually 1 over 4 pi epsilon naught. Epsilon naught is the constant of, it's either permissivity or permittivity. I believe it's permittivity. Not important right now. We'll get to that a little bit later. Okay, but ultimately, if I rearrange this guy, okay, I can see that epsilon naught, just rearranging this, moving it up here, moving Ke down, is 4 pi Ke, right? And you'll see a number right over here, which is why this exact number is written on your AP equation sheet. And now, if I take epsilon naught, this is equal to 1 over epsilon naught. So, electric flux is equal to Q over epsilon naught, meaning electric flux is directly related to how much charge is inside the Gaussian surface. Now, let me finish my thoughts here, and then I'll tackle any questions. I want to make sure and get this. Now, you see this weird shape up here. Does the fact that I drew a weird shape instead of a sphere change how many lines are leaving that particular guy right there? No. I could arbitrarily draw this whatsoever, and electric flux is directly related to how much charge is inside that ridiculous surface. If I can measure electric flux, I can weirdly measure exactly how much charge is in an object. Is it easy to measure how much charge is on a particular object? No, but this kind of gives us an opportunity on how to do that. So, this is that equation. They just changed Q to be the Q inside that Gaussian surface. So, find the electric flux through the surface in the figure. I don't even have to worry about mathing this or looking at it crazy. I can literally look at this. -3 would make lines go which way? Inward. Okay? It's -5 more lines would go inward. And this guy right over here, lines would go out. And to try to mess with this particular guy mathematically would be a pain in the arse. Yes? Or I can go -5, -8, -6. I drew a Gaussian surface such that the charge inside that surface is a total of -6. And as we said on the previous slide, electric flux is simply equal to how much charge is inside that surface divided by epsilon naught. Questions? Yes?
Didn't our equation for the height for flux come from the fact that it was a sphere, like the surface area of a sphere?
Yeah, that's what I thought too.
That's not a sphere.
No, it's not a sphere.
Please tell him to come back. I want to say hello to him.
Have Silas teach us stuff.
You can be excited without
Tell him to come back.
like physics.
Yeah, bring him back.
Silas, come back.
He's doing like
Who do you want to say hi to? What's your name? Someone says hi to someone. All right. So, the equation is not actually based on that sphere. The purpose of the sphere was to choose a weird surface that demonstrates very clearly that the number of lines or electric flux has absolutely no impact on what the shape actually is. Okay? The equation is defined by this right here. That is the equation, by definition. That's what we started with over here. Okay? There's the equation right there in a nutshell. Why? The number of lines is directly proportional to this. If I somehow chose to double the Q inside of here, would that double electric field? Yes. So would that technically double the number of lines? Yes, based on the rules we stated earlier. So would electric flux double? 100%. What this is meant to show is that you can arbitrarily choose any possible shape whatsoever. The math gets very icky, but you can't actually prove that if I turn this into a cube surrounding this guy, it will 100% remain exactly the same. This was meant to very quickly kind of verify that, and you are welcome to mathematically verify it across all sorts of weird shapes if you want that kind of stretch. But ultimately, the purpose of this is, hey, Spainhour, what if I make the radius bigger? Well, what happens to the area? Bigger. That should mean more electric flux. Except what also happens to electric field? Gets smaller. You get a smaller electric field. So how much bigger? Well, let's say I double the radius. According to this, my surface area would increase by 4 times. But how much would my electric field decrease by? 4 times. So would the number of lines actually change? Absolutely not. But again, it kind of goes back to just somewhat proving this picture as it already stands. We're trying to prove this nice simplification of a very messy system. Choose a Gaussian surface, pick a random shape, pick a cylinder, pick a whatever. Everything inside matters. Now, the next question, I think they covered it in a second. I'm almost done here. Oh, I'll get to that in just a minute. What if I've got a weird shape like this? And my positive is right here, okay? What you end up doing is you track how many lines are leaving / coming into the surface. In this particular guy right here, there is 1, 2, 3, 4, 5, 6 lines leaving, and there are 1, 2 coming into it for a total of 4 lines are leaving in total. So does it matter that it cuts through this weird shape? Well, I wouldn't choose that weird shape if I were you, but no, it doesn't. What's up?
Why are they so long on the sides?
Why are what
Like
so
the
long?
right and down were super long, but the up and left weren't.
What are you talking about?
It's just like the shape. You just drew the lines to show that the chart is going out.
Yeah.
Okay, so
Yeah. I'm sorry. I could draw them just as long. I was literally leaving the surface. All right, last one. Today took longer than I thought. I apologize, but we are done with the chapter. All right. Gaussian surface allows us to look at this right here. Electric field, okay? Electric field is force per unit charge. Yes? Okay? Electric field is also equal to, oh, come on, hold on, don't screw this up. Charge, is that right? Hold on. Electric flux is equal to Q over epsilon naught, which is equal to E over A. So, here it is. So if I just divide A underneath, E is equal to Q over A over epsilon naught. Q over A is known as charge density. This right here is charge density. And by the conversation we had a second ago, we can pretty easily measure what the electric field of an item is. So if I have the electric field of the item, according to this equation, can I measure what the charge density is on that area? What would the units of charge density be?
Q over M3.
C over
M3.
no, meters squared. Area, not volume.
Isn't density like volume?
Yes, usually it is. That's a really good point. Density can be referred to anything. We can actually, I believe, at one point in time, we can mess with linear density. Okay, linear density, area density, or volume density. Usually, we have messed with volume, but this is basically just saying how much of this thing is in a particular line or area or volume. In this particular case, we are looking at area, and thus is meters squared. All right, I am done.